Okay, so some additional concepts about matrices. If A equal to Aij is an M by N matrix and Aij is equal to 0 for all I and for all j's, then A is called a zero matrix. Hence, a zero matrix is denoted by 0. Okay, so if A is a 2 by 3 matrix where all the elements are 0, then it has 2 rows and 3 columns of zeros. 2 rows and 3 columns of zeros. So there are several zero matrices. The size of the zero matrix may vary from 1 by 1 to any size m by n. So if you are given a matrix, say K, and you add to it matrix O, whatever the size of matrix K is, say it is 3 by 4, the zero matrix is also 3 by 4, and the result will be equal to K itself, which is 3 by 4. Okay? How about the identity matrix? The identity matrix I sub n. I sub n is an n by n scalar matrix where Aij is equal to 1 for all i's that are equal to j. We know what a scalar matrix is. A scalar matrix is a diagonal matrix or a square matrix where all the elements are 0 except for the main diagonal. And if the elements along the main diagonal are all equal, then it is called a scalar matrix. A scalar matrix is a diagonal matrix. A diagonal matrix is one where all the elements are 0 except those along the main diagonal. And if all the elements along the diagonal are equal, then that is a scalar matrix. So example, say I sub 3, that will be a 3 by 3 matrix where the elements are all zeros except for those along the main diagonal, which are all equal to 1. So if it is the identity matrix of order 4, that will be a 4 by 4 matrix. So what is the relevance of this identity matrix? The identity matrix is such that if you are given any matrix A of any size, A times I equal to I times A equal to the matrix itself, right? So that is the definition of the identity matrix. It is a matrix such that when you multiply it to any matrix A, or any matrix A is multiplied to that matrix I, the result is the matrix itself, or the result is equal to the original matrix. So let us have an example. Given matrix A, 3, 1, 2, negative 1, 1, and 0, which is a 3 by 2 matrix, let us verify if AI is equal to IA equal to A. So let's start with AI. Let us rewrite A, 3, 1, 2, negative 1, and 1, 0. And it is a 3 by 2 matrix. So what must be the size of matrix I, or the identity matrix? There is a requirement when it comes to the product of two matrices, no? That the number of columns of A must equal to the number of rows of matrix I. So in this case, we will be using the identity matrix I sub 2. So we multiply it to a 2 by 2 identity matrix. And what do we get? 3 times 1 plus 1 times 0 gives us 3. 3 times 0 plus 1 times 1 gives us 1. Second row to first column. 2 times 1, negative 1 times 0 is 2. Second row, second column. 2 times 0, negative 1 times 1 is negative 1. Third row, first column. 1 times 1 plus 0 times 0 is 1. And finally, third row to second column. 1 times 0 is 1. 0 times 1. 1 times 0 plus 0 times 1 is 0. And we see that this is equal to matrix A. How about I multiplied to A? Now, let me write A first. 3, 1, 2, negative 1, 1, 0. It is a 3 by 2 matrix. So, the number of columns or the number of rows of A is 3. So, what must be the size of matrix I? It must be the identity matrix of order 3. So, 1, 0, 0, 0, 1, 0, 0, 0, 1. Multiplied together, 1, 0, 0 multiplied to 3, 2, 1, correspondingly will give us 3. 1, 0, 0 multiplied to 1, negative 1, 0 will give us 1. Next, second row of I, 0, 1, 0 multiplied to 3, 2, 1, that will be 2. 0, 1, 0 multiplied to 1, negative 1, 0 is negative 1. And for the last row of the product, it will give us 1, 0. Again, that equals matrix A. Alright? So, I is the identity matrix. It is a square matrix. It is a square matrix and a scalar matrix where the elements along the diagonal are all equal to 1. Now we go to the different elementary row operations. Now these are operations that will manipulate a given matrix. So elementary row operations. We're given matrix A equal to Aij. An elementary row operation, on matrix A is any of the following operations. The first one is interchanging two rows. So when you interchange two rows of A, that is an elementary row operation. The second one is multiplying a row of A by a non-zero scalar. If you multiply one particular row of A by a non-zero number or a non-zero scalar, that operation is an elementary row operation. And finally, adding to a row R of A k multiple of row S of A. So another elementary row operation is when you multiply a row of matrix A and then adding it to, again, if we add to a row of A k multiple of another row of A, that in itself is an elementary row operation. Okay? So once again, an elementary row operation is any one of these three. When you interchange two rows, when you multiply a row by a non-zero scalar, and when you add to a row a multiple of another row. Let us have an example. Given matrix A, 3, 1, 2, 0, negative 1, 1, negative 1, 0, 1, 0, 2, 1, 1, 3, negative 1, 0. Let me add another column of 1, negative 2, 1, negative 3. Okay, so we have here a 4 by 5 matrix A. We perform the following elementary row operations. Elementary row operations. Let me insert here sequentially. So we perform sequentially the following elementary row operations on A. First one, let us interchange rows 3 and 4. Then multiply row 2 by negative 1. Next, add to row 3 2 times row 4. Number 4, we add to row 1 negative 3 times row, let me see, row 3. Okay, and finally, you interchange rows 1 and 4. Okay, so we will do it sequentially. So let us perform the first operation. We interchange rows 3 and 4. So let us call the resulting matrix as A sub 1 because it will be different from matrix A. Now, when you interchange rows and 3 and 4, you will come up with another matrix. So let us label it or name it as A sub 1. So we will copy rows 3 and, or rather, we will retain rows 1 and 2. 3, 1, 2, 0, and 1. Negative 1, 1, negative 1, 0, negative 2. And our new row 3 will be 1, 3, negative 1, 0, negative 3. And our new row 4 will be 1, 0, 2, 1, and 1. Okay? So that is our A1. Now, the second operation, we multiply row 2 by negative 1, so it will result to another matrix, call it as A sub 2. So, since we will work on row 2, all the other rows will be retained. So, row 1 will be retained, 3, 1, 2, 0, 1. But our row 2, each element of row 2 is now multiplied by negative 1. So it becomes positive 1, negative 1, positive 1, 0, and positive 2. We retain the other two rows, rows 3 and 4. 1, 3, negative 1, 0, negative 3, and 1, 0, 2, 1, and 1. Alright? We go to the third. We add to row 3 2 times row 4. Okay? So it will result to matrix A sub 3. Let me create a space. Okay. So we continue here. A3. We will be adding to row 3. We add to row 3 2 times row 4. Okay? So 2 times row 4 is added to R3. And the result is written in row 3. Alright? You multiply row 4 by 2 and add it to row 3. The result is written along row 3. So we will be retaining rows 1 and 2. 3, 1, 2, 0, 1. Second row 1, negative 1, 0. Okay? That should be 1, 1, negative 1, 1, 0, 2. Then row 4 actually is retained. Row 4 is retained. 1, 0, 2, 1, 1. It is row 4 which is multiplied by 2 added to row 3. So multiply row 4 by 2, add it to row 3. So let's start with this element 1. So 1 times 2 is 2 plus 1. That will be 3. Next, 0 times 2 added to 3 is 3. 2 times 2 is 4, added to negative 1 is 3. 1 times 2 added to 0 is 2. 1 times 2 is 2, added to negative 3 is negative 1. Okay? So row 4 is multiplied. Let me change the direction. Let me change the position of the arrow here. Okay, let me change this. So in here, you multiply row 4 by 2 and add it to row 3. The result is written in row 3. That is exactly what we have done. Then, number 4, create another space. We add to row 1 negative 3 times row 3. We add to row 1 3 times of row 3. So let us indicate it here. Row 3 is multiplied by negative 3. And we are going to add it to row 1. It returns to row 1. So the result is written to that row where the multiple of another row was added. So that gives us A4. So the unaffected rows are 2 and 4, okay, as well as 3. So we shall retain rows 2, 3, and 4. 1, negative 1, 1, 0, 2, 3, 3, 3, 2, negative 1, 1, 0, 2, 1, and 1. Okay? Each element of row 3 is multiplied by negative 3. Everything here is multiplied by negative 3, and then we add it to row 1. So 3 times negative 3 is negative 9, plus 3 is negative 6. Okay? Negative 9 and 3 is negative 6. Next, 3 times negative 3 is negative 9, plus 1 is negative 8. 3 times negative 3 is negative 9, and 2 is negative 7. 2 times negative 3 is negative 6, plus 0 is negative 6. Negative 1 times negative 3 is positive 3, and 1 is 4. So that is our A sub 4. And finally, we will interchange rows 1 and 4. So we will interchange rows 1 and 4. And what do we get? So let us erase this part. And we will be getting another matrix and label it as A sub 5. So our new row 1 will be 1, 0, 2, 1, and 1. Rows 2 and 3 are retained. And our new row 4 is negative 6, negative 8, negative 7, negative 6, and 4. Okay? We have the following definition. A matrix B is row equivalent to matrix A if B can be obtained from A by applying a finite sequence of elementary row operations to A. So in our previous example, A1 was obtained from A uh, by interchanging two rows. So we say that A1 is row equivalent to A. A2 was obtained from A1, so we say that A2 is row equivalent to A1. A3 was obtained from A2, hence A3 is row equivalent to A2, and so on and so forth. So in other words, all the AIs are row equivalent to the other AIs. No? As A5 is row equivalent to A, as A3 is row equivalent to A1. So all the AIs are row equivalent to each other. Again, we say that the matrix is row equivalent to another matrix. No? A matrix B is row equivalent to another matrix A if that matrix B can be obtained from A by applying a finite sequence of elementary row operations to